No. Okay. The district was paying for us to have Zoom as long as we wanted, and it's sometime in the last month they stopped paying the bill. So I bought it myself, and I paid for it for April and May, and then I got to remember to drop it. All right, so now we are recording. Yes, you are share screening, and we are recording. Just double check that. How do I know I'm recording? Stop share. Oh, there it is. Okay. So this is spring 2023, and we're looking at test 5B, both take-home tests, but we're mostly going to concentrate on the second one because we've different than I've done in the years past. We actually go over the problems every day that it's due. So this should go pretty fast. I have not written the test. I'll probably start. I got to grade your, I got to put the grades in tonight. And I've got a grade. I just got finished grading your take-home test part A. So that grade's in the grade book. I still a lot of zeros though. Still people didn't turn it in. And so I will grade your black and blue when we're done here, put all the grades in, and then if I have time, I'll start the test tonight, start writing the test tonight. So this is helping me talking to you all. Bounce, you're my soundboard, right? So bouncing ideas off of you as to which ones I'm going to put. So I'll throw some Easter eggs in here, I guess, since you all are watching it. I thought about doing a live or just live Easter eggs, but come on, some people can't. Some people are working; they can't make it to this. So they got a baseball game or something. So that's not fair. So I'll record everything. Okay. Thought we'd have a bigger crowd here, but that's all right. I really do. I think that doing it in class, people don't feel like they need to come to these things, which is cool. All right. Number one, old stuff. Now, this is last week. I'm going to go through this kind of quick since it's old stuff. But certainly, yes, that one I would put a check mark by. I'm going to put a check mark by it. I'm going to put a red check. And that means that I'm going to probably include that one. A good chance, something like that on the test, because it's your basic Newton's original second law. Any questions on there? Impulse, it's just all, force equals delta P over T, and then bring the T over, and now you have impulse, force times time, which is the same thing as delta P, same thing as change in momentum, okay? Also on this one, be advised that if you have an I roof or a J roof in the answer, you're going to have an I roof or J roof in the problem. Okay, in the problem, you're going to have the same thing in the answer. All right, so got to watch out for that. Here, see, it's I roof in the answer and I roof, unless you're looking for time. Time's not a vector. All right. Number two, there'll be free bodies. On test 5A, we had a free body with a car. So my guess is, I might put something like number 3. I'll put a red check by number 3. That would be, it's not going to be as easy as number 2. I think it's more like number 3, where there's like 6 forces involved. And realize that it's equal to 0, okay? So be careful. If there's no acceleration, set that thing equal to 0. But no numbers here. Also, don't forget your yellow big. If it's horizontal, we do a big yellow arrow. If it's at an angle, we do the dashed line. Okay. And I'm just going to blow on through this unless you guys in the meeting chat over there type in something. We haven't been tested over this yet. I guess not. Anyway, so just on the take home. So yeah, if I can squeeze this in there, that's certainly going to be on there. I mean, I only have so much room, so I don't know. I don't know. I'm not going to put a red check there. A red check means there's a pretty good chance I'll include it on the test, but I just don't think I'll have room for this. Just the idea that the bottom part, maybe a little quick question, multiple choice or true false, not true false, hate true false. Maybe some kind of multiple choice, but where is the wheel rotating about? And the answer would be the bottom of the wheel. The point of contact between the wheel and the ground is the axis of rotation for a rolling wheel. Something like that. I don't have a lot of room. 5 cycloid patterns. If you look at the reference sheet, I added at Stella's last night, I added the brachistone, which is I can't really say it right. Brachichromostone. It's the 2 points. The shortest distance between 2 points is a straight line. The shortest time between 2 points, if gravity is the only force involved, is a cycloid pattern. And so if you look on the reference sheet, I forget which one it is, 62, 63, somewhere in there. It has the little beads. It has four points of the bead sliding down. I don't know that would be on there, but the idea that the reason why we go over it is these points right here, it stabs the ground, right? And so that's why we can say that it's F sub S and not F sub K. Don't close this. Oh my gosh. Okay. Okay, I don't see any comments. We're gonna keep moving. Number 6, we've talked about this in class. It is nasty. There will be a gold standard problem. I just don't know. I don't think it'll involve, well, this is terminal velocity. That's a new concept. It could involve that. It's either, okay, I'll tell you this. Here's an Easter egg. The gold standard on the test, gold standard unit analysis will either be VT, which is terminal velocity, or it'll be force of thrust, M dot VE. Now that's not earth shattering because that's what the two were on the take home, but there will be one on there and it'll be one of the two. Okay, because I haven't written it yet, so I don't know. But it'll be one of that's what it'll be. It won't be some crazy, find the energy in a nuclear bomb kind of thing. It'll be one of those two. So very similar to the two that we've already done. We'll look at that. The last thing we do tonight is we'll look at that last one. On this one, it's the same gold standard kind of idea we've been doing since September. Oh, just one caution. I would leave off. I would stop, below. Don't go below the red. There's no reason to on a test unless you just have the luxury of time, which, as we know, we don't usually have on a test. I would stop. I wouldn't do any calculations. I'm going to go through and check all your stuff anyway. So it does make my life easier if you have an answer. I can just see if your answer's right and then quick double check and give you full credit. But please don't do that unless you are done with everything else. Then go back and do it. That's just a smart test taking. Triage. Number 7, I put traces on here, and I think this is traces, and I think it is. It looks like his writing. And then I realized when I was looking at this, and I was looking at the one, the second one I wrote it wasn't supposed to be about drag. It was supposed to be about lift. I don't know what my problem was. So both essay questions were about drag, slightly different asked questions. But it's all about laminar flow, and really Trace did a better job than I would have done, and much cleaner writing and a good thorough explanation. So yeah, if there's an essay question, it will be about this, about wake zone, and as much time as we spend on it, I'm going to have to put a problem on there just to justify all those days that we went through over and over again: tennis balls, golf balls, racket balls. Because drag is a pretty big deal. I didn't get much about lift, which is my dumb fault. Anyway, lift is still sort of the same, still airflow, faster airflow above, slower airflow below. We watched those dragsters, fly today because too much lift. Okay. So it's sort of the same concept: airflow, turbulence, above a wing, where the separation point is. So a lot of the same concepts, only it causes lift, which this doesn't really talk about. This talks about drag, but fair enough. Yes, 100%. Oh, let me go back and check that, because there'll be something along these lines. I'm going to check the second one, though, the second essay. Anyway, this one certainly double, triple check. Yes, 100%. One like this one, or the one we talked about today in class, where you have to first draw the forces, then do the head to tail, then do the free body, and then do the equation. So yeah, those 4 things you'll have to do on at least one problem, maybe 2. Because remember, the number 1 thing you're supposed to know out of this class is vectors, and the number 2 thing is free body diagrams, and probably the number 3 thing is gold standard. So if you're really good at those 3 things, you're fine in engineering or wherever you go into. But this one, I'll take various answers. They're kind of hard to grade, because you just, as long as you follow the rules, though, we're gonna have 55 different answers on the test, and they might all be right. Okay, so once you get your free body, just drag and drop or redraw those over there on your free body diagram. Once you get the head to tail, then redraw those in your free body. Okay, let's keep going. Unless you guys can stop me by just asking a question. Number 9, and I'm going over these fast because we've already kind of gone over them in class, but this is just to put it all together in one video. Number 9, let's see, rockets launching. Is there any kind of M dot on there? I don't see an M dot. Normally on a test, I would put, now it does have M bar. Remember, M bar, if you have a rocket and you have thrust involved, you always need to refer to the mass as the average mass. And here I say that, and I think on one of the problems on the homework, on the take-home test, I didn't, but I'll correct that. And then, don't miss that freebie point. But if you have to put a dot, you have to put something down. You can't just leave it blank. Probably not going to have this one. I wouldn't worry about this one because there's no angle involved. So I don't think this would be on there. Now we get to the current take-home test, and I'll blow this up a little bit in case you're watching on your phone. Remember this little dipsy do, you got to do this little squiggly if you're saying that your vectors, if you're running out of room, you want to make your vector longer. This is buoyancy. Remember, buoyancy is always straight up. There will be a buoyancy problem. We'll talk more about buoyancy more tomorrow. I've been doing so much with history lately. But tomorrow I'm going to go quick through history and then get to the buoyancy and finish up 5.6. We're obviously not going to finish 5.7. Don't worry about it. Don't worry about it. Whatever we get done tomorrow, we get done. Otherwise, yeah, I'll kind of mesh it into packet 6 a little bit. Okay. So yeah, I do want to put a question on there on buoyancy, so I'll check that one. Notice that they're equal to 0 because, knots is not acceleration, so it's not speeding up or slowing down. It's going at a constant rate, and so no acceleration, so they're equal to 0. That you don't want to lose those points. Buoyancy is always straight up, mg always straight down, drag always to the opposite direction of motion. I didn't show DOM, I just noticed. So I should have shown DOM with an arrow, big fat arrow, big fat yellow arrow. Show DOM. Okay. Number 11, blow that up. Number 11. Now this someone pointed out that I didn't follow my own instructions. I said do head to tail, and I did a free body. I kind of did half head to tail, half free body, because that part right there, that green kind of semi-ghost was mg. That's how I knew how much angle to make my force of thrust, because I needed to include the mg. The only thing that wouldn't be cruising along, wouldn't need a higher thrust, would be a photon, which wouldn't have thrust. but because there's no m dot, but you have to have some kind of mass to your rocket. And so the thrust always has to be greater than the direction of motion, unless there's like wind involved or something, like in our helium balloon with the pinhole leak. Drag always opposite direction of motion here. Notice I'm saying m bar, okay, because mass is being shot out the back, and so it's changing. So you look at a particular time frame, say 5 seconds of thrust. Okay, now what's my average mass during those 5 seconds? Okay, but more on that on number 17. So yeah, I mean, there will be it probably won't be a car on a road. It'll probably be, thrust, those kind of things. Higher order thinking. You do have acceleration here, so you got to say max, may. Any questions on that? All right, then we get to impulse. Yes, certainly there'll be an impulse where probably you have a trapezoid or something, and you're going to have to come up with the area. I'm not going to make you do the integral and antiderivatives. That was just kind of for fun. Oh, the other thing is watch it on this one, because this definitely, I think I already have the problem I'm going to pull for this one. That's a big yes, because it's important that you understand the idea of the impulse is multifaceted. I mean, it's involved in so much in physics. It's involved obviously in force. It's involved in this area. It's involved in momentum. It's sort of a big link between time, momentum, force. All these things are involved in impulse and everyday life. I mean, impulsive force versus non-impulsive force. So it's everywhere. So yeah, this will be on there. Now, my suggestion, like suppose I make this pounds on the test, and I make this minutes, some weird thing. Well, then just plot the area and call it pound minutes, okay? Don't turn it all back into Newton dot seconds. It's not necessary that you follow MKS unless it says to. All right. Oh, and then the average, remember the time averaged force here, that F bar. You can't just look at your graph unless it's a rectangle, which it won't be. It'll either be a trapezoid or a triangle. Triangles are what we're using. Triangles with small bases is what we're using to mimic a impulsive force, normally a bell-shaped curve, which that formula is crazy. And then instead of mimicking a more flat, longer duration force, we're using trapezoids, okay? And I haven't decided whether it's a trapezoid or a triangle. But either way, the average force is not going to be halfway. You're going to get like 1 out of 10 points for that, because you should know better. The average force has to be found this way. Always find the average force, F bar, by taking the impulse over delta t, which is this graph is basically the area over change in time. That's how you find the average force. So in this case, it's 24.6 newtons. Now to represent that, that is a rectangle. The yellow rectangle is a horrible representation of that trapezoid, but it's algebra versus calculus, as in geometrical calculus, because we're not really doing integrals, but still we're finding area. So obviously the trapezoid is a much better representation of the force. There's a lead in, there's a fade out, than a stupid rectangle, but algebra can't handle that area like that. So we have to make it a trapezoid. So we call it time averaged force. Okay. Oh, Sargo says, why did we not count the first 20 milliseconds? Oh, because so Sargo said, well, wait a minute. What about the first 20 milliseconds? Nothing's happening. So you go, well, why didn't you start at 0? Because perhaps they were monitoring something, looking for a collision, and nothing happened in the first 20 milliseconds. Okay, then something happened. So then the two came in contact with each other. So yes, you could shift your graph, but that's not what we did here. So I think I'm just trying to emphasize the point that there's a beginning. It doesn't always start at 0. Okay. All right. This one, no, this is a no. Don't waste your time. No, it wouldn't be a waste of time, but I can't fit it on there. I mean, it was cool to talk about, derivatives and slope of force versus time, but we didn't have time to explore that very much. And it's cool to talk about integrals. But the reason is but no, it won't be on there. The reason is because sometimes the graph looks like this, and you got to find, it won't be on the test, but I mean, in AP physics or something, you got to find this area here, and you can use an approximation. You can say, well, that's kind of like two rectangles, big rectangle, and a little, you get close, but to get the exact, you had to use antiderivatives. But don't worry about it. I just wanted to introduce that idea to you, but that 13, don't worry about. Okay. 14, I think we looked at this one today, 14A. Okay. So I did this on purpose, having the car go to the left, which we are calling negative. I said to the left is negative. I didn't say on the problem, but that's, you have to have which one's plus or minus. The default is to the left is negative. Now, if you came back at me and said, nah, I'm going to say the default is direction of motion is positive, then but the thing is, it says right there, it says negative 35, I'll go red, negative 35, negative 10, you know what I'm saying? So it is slowing down. It's going from, okay, it's moving from negative 35 meters per second to the left to negative 10 meters per second to the left. Well, that is slowing down, but the difference is positive. See, this is your M, this is your mass. Oops, sorry. This is your mass times delta V. Well, V final minus V naught. V final is negative 10, V naught's negative 35. I subtract those two, I get positive 25, positive 25. And so the impulse is a vector. It's not a force, it's a force through time that is slowing the car down. And so all I know is impulse, the change in momentum is 57,500 kilogram dot meter per second. So that's a lot. That's a lot of impulse, but it takes a lot of impulse. Sargo asked here, said, so the velocity is increasing in the something direction, in the positive direction. Velocity I see on this one is decreasing. No. Okay. I think I see where you're going with this. Your delta V is okay. Great. I'm glad you asked that question. So that's a stamp question. So the delta V is positive 25. You say, wait, I mean, it's speeding up? No. From this weird orientation, it is slowing down. The speed is slowing down. But the velocity has gone from a negative 35 fast to negative 10. So it's slowing down, but it's slowing down in the negative direction, which means acceleration is in the positive direction, right? The force that's causing it to slow down is going to the right. And so that means, so impulse is one of the questions they ask you on tests is impulse, like they'll say, what direction is impulse? And one answer will be in the direction of momentum. That's false. That's false. Impulse is in the direction of change in momentum. Okay. Bill Fix, who was the teacher before me, that would always be one of his true false questions. Impulse in the direction of momentum. Kids would say true. And they would accuse him of being tricky, but no, really, it's in the change of, it's the change in momentum is the direction that impulse is in. So impulse here, the change in momentum was positive because it was going in the negative direction. it's enough to make your head spin, but that you've got to keep your head on a swivel here and draw it. Those of you that refuse to draw much, your drawings look like this. Okay, there's your drawing. That's why you don't get it, because you're not really you're not visualizing. And I know some people aren't visual, and it's really hard to do physics if you aren't visual. And more power to you if you're still in here and you're not a visual person, because physics is a very visual science. I don't know how you can do it without, I mean, just putting in numbers and stuff and not really seeing what's happening. I would be absolutely lost. So you have to that's why the drawing is so important. Okay. Anyway, impulse is positive 57, which means if that thing is going to the left, it's pushing it back to the right. It's the tendency is to make it go back to the right. So it has enough momentum to keep going, but it slows down. All right. And then part B says, well, this whole thing occurred in 750 milliseconds, which I think if I could go back and write that again, I'd probably say something like 3 seconds, because 750 milliseconds is really, really short amount of time to stop a car. A car is going to stop in less than a second. That's not much of there's no cushion there. I would think people are in big trouble, because that's like hitting a brick wall. What's it say? Civil engineer, as if so, this civil engineer designed a terrible water barrel system. Although if the car's going fast, I could see it stopping pretty quickly. But really, 750 milliseconds is, I think I was pushing it a little there. If I could rewrite it, I'd say 3 seconds. But anyway, I didn't. And so that makes, once again, F bar is the impulse over the change in time. And so since change in time is 0.75, you divide that, you get 77,000 newtons. Can you imagine? I mean, 77,000 newtons, that's a lot of G forces. I hope it's a good seatbelt. Now, what I told 1 hour was, I might ask you to, here's an Easter egg. I might ask you to graph it, graph that. Oh, great. I might ask you to graph the F bar, and then graph a possible or a likely F versus T. So that's what I'm showing here. The purple, like the purple here on this one would be, okay, this purple part, this would be your 70s. If this is kilonewtons, this would be 77 would be that dashed line. Okay. And then you would say, well, but we know that's average. So this area here, the purple rectangular area, would have to equal the area under the blue curve. And so I would take, a lot there. But if that sounds impulsive to me, that's pretty much an impulsive force. So then you make kind of a bell-shaped curve and have some kind of F max up here. I don't know. I may do this. I may not. F max. And if this doesn't make any sense, you can ask me a question about tomorrow. And so you would say, well, I'm going to say my F max is 200 kilonewtons. Okay. Because it's going to be a lot bigger. Just as long as the blue, when you take that blue area, it's the same as the purple area. Okay. So with mental scissors, I cut out that and I cut out that and I say, okay, does that kind of fit up there? So anyway, that's what I was thinking that I might do on the test. Because remember, I can hold back 30%, and that would be my quote surprise. Maybe a surprise I throw at you. Okay. Oh, by the way, the history. We've spent an inordinate amount of time on history because it's interesting. History on this week. So remember, for history, that it's for a part A, it's plus or minus 12, but for 5B, like it was in 4B, it'll be plus 16 up to plus 16, and that's for the history, or a minus 24. So I've increased the penalty a little more, but I've added some to the bonus. And still on 4B, when I did this, by far, people were getting bonus still. So just keep that in mind. All right. So do look over the history. There is some penalty if you don't. Okay, then we get to 15. This is the one more like probably the format you'll see. It's the same as number 8 was, but check, 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 5 checks, definitely going to be on there. Where this may not be a helium balloon, it might be a rocket, or it'll be something. I guess I could put something in water, like I have done that before, where it's something rising in water, like you pick a volleyball and it's in a, oh, I think the one I did last year or 2 years ago, there was a volleyball in a stream. Okay, so someone had pushed a volleyball down to the bottom of the stream and then let it go, and so there was a stream current this way. There was a buoyant force of water up, and then there's water drag, so they had to kind of figure it out that way. Okay, I don't know, I'm just saying I'll try and make it similar to these kind of problems, but you know, you can only do so many helium balloon problems. So first thing you got to do is, you know, write this out, just kind of lay out your forces. You do have to honor, if it says 10 degrees, then you got to make force of wind 10 degrees. Mg always down, BA or BW, whichever it is, always up. Drag always opposite direction of motion. And then this one has thrust because helium balloons don't have thrust, except it has a pinhole in it, so it's shooting out helium. So it's acting like a jet. It's acting like a rocket. And so there's that. And then, of course, you have to say, well, it's accelerating, so there's a summation of forces. Okay. Then we go down here. We then do the head to tail. This is the hardest part, or the most important part, is get your head to tail right. The free body is easy once you get the head to tail. So all the stuff we talked about in class today. But when you're doing your head to tail, the first thing you do is you draw your summation of forces, assuming there is summation of forces. Maybe the twist on the test will be that the balloon is rising at a constant rate, or whatever it is. Ball, balloon, rocket, whatever it is going at a constant rate. In that case, there wouldn't be a summation of forces. Okay, there's no acceleration. And so all your vectors will just connect up. My guess is I'll make a summation of forces, because I want you to be able to realize that if you put a summation of forces vector on a head to tail, but you don't put it, see, I didn't put it on the free body. That red arrow didn't make it over the free body. Also, notice on the free body, you need that DOM. I don't need a DOM on head to tail because I have the summation of forces in my DOM. I'm not going to take off if he did. I guess you can make the argument, well, then you don't need a DOM on a free body either, because the RA, but that's not kosher, man. Put a DOM on a free body diagram. I want you guys to be like the ace kid in the physics class in college, and to show your free body diagram prowess, you should put a DOM on it. Okay, and then all this was, I just followed the rules, you know, buoyancy up, mg down, et cetera, et cetera. The ace in the hole is the force of thrust, as we talked about today. Okay, and then finally you do your equations. Now we should all have the same equation. The only thing that's going to be different from yours and mine is the angle on the force of thrust, because that's just something you throw in to make it all work. You don't have any limitations on length or angle for force of thrust. So that's your ace in the hole. So mine, I just looked at, I did a protractor and found that it was 10 degrees. Okay, there's those. Okay. Remember cosine, all my angles, I promise you on the test, all angles will be from the horizontal. So X will always be cosine, Y will always be sine, always. Also remember, drag is always opposing motion. Wind may oppose, wind may help. Like, look at this, check this out. Wind hurt. And the other thing we brought up in, I think it was third hour today, was that no longer do you say that to the right is positive, up is positive, down is negative, to the left is negative. That works for projectile motion, those kind of things, but not when there's forces involved. As we'll find out if we get to pulleys, I hope we do in May. Direction of motion is what's positive. Now, you can't do that when you do conservation of momentum, because you have two things you have to establish. In a conservation of momentum, you have to establish a positive and a negative direction and keep that through the whole collision. But when it's just a free body, when there's one body, right, you can't have a collision with one body. When you have a free body diagram, the direction of motion is always positive. That is a fundamental rule of free body diagrams. So because of that, drag is always negative, and solo cup physics, which I still need to bring my solo cup up, solo cup physics, drag always drains energy out of a system. Packet 6, we get into energy and work. And friction, kinetic friction, always pulls energy out of a system. Wind, look. In the X component, wind pulled energy out, but in the Y component, it adds energy to it. So that can happen. Buoyancy, and I showed one class, I think it was third hour, where you drop the balloon. In that case, buoyancy is negative. It's pulling energy out of the system. But normally buoyancy, something's rising, and so buoyancy is trying to add energy to the system. Same thing with weight. Sometimes weight, if it's falling, weight's adding energy, meaning that it's speeding it up. It's trying to make it speed up, like something free falling, or say a skydiver. But if it's rising, mg, the weight is pulling energy out of the system. It doesn't want it to rise, right? So the point is that the RA is always, and friction are always going to be negative. If you ever see yourself adding drag, you made a mistake. Okay. Back to Trace's. He did a magnificent job here. I just put this on the screenshots today and blow this up. So kudos to you, Trace. You have a future in physics art. You know, I think that there should be this is what I may do when I retire, become a physics artist. Trace should consider this as well. You know, because look at this, you had a little cutter there in the wake. So with a golf ball, it's hard to see, with a golf ball there, he's right. The weight, the separation points, as he showed here, separation points push back because of those little divots. The air is more attached with little eddy currents. It's attached to the golf ball longer, which makes the wake zone smaller, which makes the low pressure zone smaller, because turbulence is low pressure, makes the low pressure zone smaller. And therefore the difference between the low pressure zone behind the ball and the high pressure zone, because of the laminar flow in front of the ball, the difference is not as great, and so less drag. So a golf ball goes further. I think Sebastian said 316 or so divots is standard. Cheaters will have 420 or more than, something like that. So if your buddy all of a sudden is golfing and all of a sudden she's driving the ball, an extra 20 yards, you got to go start counting those divots. Now a racquetball, the one in the middle is a racquetball. There's no divots, there's no fur, there's nothing, and that thing is smooth, and so its separation point, as Trey's showing, is much further up. So therefore, a much bigger wake, like in behind a boat. Therefore, a bigger low pressure zone. So the difference between the front and the back is greater, therefore more drag. Okay. And then for a tennis ball is, I think second hour was asking, well, what's the difference between golf ball, tennis ball? It depends. I mean, the point is both those have a small wake zone, as Trey showed. I'm going to send this picture on over to Mr. Patrick so he can use it next year. And Trace will become a physics celebrity. All right. Don't copyright it. Don't trademark it. Oh, question. I've got to be honest. I don't think that's mine. Oh, well, if that's not yours, Trace, I don't. Whose is it? Is this Megan's? Megan, is this one yours? I thought that was Trace. No, Megan says it's not hers. Well, now I'm curious. Okay. Whoever the mystery student is, please come forward. Megan had a good one. Oh, Trace said I drew mine with the DOM. Oh, that's right. That's right. You're not the only one. A lot of people had it backwards, but everything was a great picture, but it's backwards. And what I said to do was just switch the arrow. Golly. Okay, well, I'm doing somebody some injustice. All right, we'll get it figured out. Now something new. Hey, okay, why you came tonight? It was number 17 and 18. So let's look at 17 and let's diagnose that. And I might be wrong. I just let's find out if I'm right or wrong. There's a real good chance because I don't pay attention to punching in numbers. But that's any questions here. That's my free body. I'm just following. All this is just following what the problem said. Now, once again, it's a rocket, so you use M-bar. I made this problem up last week, and I probably need some tweaking, but I think it's a pretty good problem. DOM is 60 degrees, but the rocket says it's going at 75. That makes sense, right? It does, yeah, 75 above right horizontal. I put things that are forces are in blue, things that aren't are in purple, because you don't want to get confusing. It's confusing enough. M bar G is 1100. Now, where did I get that? That's the question. Where did that come from? There's no 1100 in the problem. Why did I say 1100? Anybody want to answer that? Why would I say 1100 when it's not even the problem? The hint is it's M bar G. Yes, and Shargo got to it first. Sargo did. He said, well, the thing starts off at 1300, it ends up at 900, so the average mass is 1100. Okay, so that's why it's called M bar G, because it's losing mass. You know, in 8 seconds, it lost 400 newtons worth of weight. So whatever that is in mass, it lost a lot of weight because it's spitting it out the back, you know. Okay, so let's keep going then. Next thing is to come up with your equation. Well, the force, I'm just going off the drawing. We're trying to figure out what now notice the question says, what was the gain and altitude of the rocket? Gain and altitude. In other words, I only care about the Y direction. I don't care about the X direction. Okay, it actually made your life easier because you don't have to do inverse tangent stuff. It's just, in other words, what's the vertical? How high up does it go in those 8 seconds? So I only looked at, over here in the equation, I only looked at the Y component. So we say FT sine 75. Okay, that gives me the Y component of that triangle. M bar G, because that's in the vertical direction, minus, and then minus the drag, the vertical component, which is RA sine 60. Now, that's the only 3 forces there are, but you're only looking at the sines, not the cosines, okay? No need for cosine in this problem. Equals MAY. I'm trying to find out how far, I'm trying to find delta Y, but I can't find that in one equation. I'm going to have to first find AY and then use orange kinematics vertically to find out the delta Y. Okay, so then I worked that. I would all the rest, this next step is just running the numbers. And hopefully I did it right. Anybody else get 7.72? Anybody else get 7.72 here? Okay, fine. I'm thinking my math is right, so I'm just solving for AY. I had to get the 1100 newtons into kilograms. And if I did my math right, I wasn't in radians or something, I think I'm okay. So we got an AY of 7.72 meters per second squared, and then it becomes kinematics. Now I'm done with forces, and so now I'm just going to use the I'm using the second orange, not second blue. Okay, it's not in free fall, but I'm using second orange vertically. So I have I need the, okay, so it said on the problem, it said that, I told you this is one of the hardest problems I've written this year. It said the object was going 250 meters a second initially, but I want the Y component of that. So I said 250 sine 60. Okay, that's the initial V naught Y plus times time, which is 8 seconds. It said it burns for 8 seconds, plus 1/2 AY, which is 7.72, times that 8 seconds squared, right? Just the second orange, but vertical. And so if my math is right, that's what I get. And I get a delta Y of 1,979 meters. Okay, so it went up almost 2 kilometers in 8 seconds. This rocket rose in altitude almost 2 kilometers. Okay, but that's a lot of thrust, so it makes sense. And then the second part of the question is pretty easy, I guess, sort of easy. It says, what is the average escape velocity? So it's just force of thrust is m dot VE. I'm solving for VE. I'm solving for escape velocity. So my thrust is right out of the problem, 2,250 newtons. My m dot is my m dot is change in mass over time. Well, it lost 400 newtons, but I have to convert that to kilograms. That's why I divided by 9.81, and it lost that in 8 seconds. And I put it negative, but it doesn't really matter. I guess I can leave that negative in there. That's fine. Negative, and I make it negative. Negative relative to the direction of motion, because the gas is coming out the back way, so it's coming out negative to the direction of motion. Anyway, so if my numbers are right, it's coming out at about Mach 442 is about Mach 1.3, which just makes sense. That gases escape really quick out the back of a rocket. Okay. Okay, any questions on that one? I'll let you sink your teeth into that. There's the whole thing, if you just wanted one screenshot of it. But I think that's a hard problem. Now, you go, whoa, is that going to be on the test? Oh, I don't know. I mean, maybe an easier version of it or something. I'll warn you guys if that's looking like it's going to make it or something like that, then I'll warn you on the group me Wednesday night, I guess. Be looking. All right, finally we get to the last one here, and we're going to make it in an hour. And this is number 18, the good old gold standard, but this is a hard gold standard. Once again, it's that force of thrust. So I've done a lot of force thrust problems. So, I'd like to say it's not rocket science, but this kind of is rocket science. So here we are trying to figure out what is the escape, how much mass is coming out, what's the mass flow, how much mass is coming out the back of this rocket. And so I just jotted down some stuff, not much of a drawing to it, but I jotted down what I knew. It's just collect your thoughts, And then I gave a hint, you'll need to combine the thrust equation and Newton's original second law. So I wrote down the thrust equation, I wrote down Newton's original second law, and then just set them equal to each other, see? That's really m bar because it's a rocket escaping mass. So m bar delta V over T is equal to m dot VE. And that's where I have a problem with my writing here. I should have said it has an average. I should have said an average mass. So I've already changed this, and for Mr. Patrick, if this occurs on one of his tests, say an average mass of 200 slugs, because we know mass is not constant. Anyway, so I end up with that equation. I'm isolating the m dot, and if I did that right, yes, I'm okay. I isolate that m dot, okay? So then the next step is to put down my givens. And so my m bar, or m, is 200 slugs. My delta V, it went from Mach 4 to Mach 12, 12 times the speed of sound. And so it went up Mach 8 in that 3 days, took it 3 days. Ion engines are used by NASA, but the accelerations are pretty small, but there's no air drag in space. And so ion engines are really interesting how they shoot out, the ions, but it doesn't need a lot of thrust. It does it over long periods of time. It's not like shooting out huge amounts of gas, like on a Saturn V. It's kind of slowly accelerating you. It took it 3 days to speed up to Mach 12. Anyway, the change in velocity is Mach 8. The time is 3 days. And then the VE is 3.5 kilometers per second. So it's coming out. That velocity is coming out pretty fast. Okay. And now we're trying to find flow rate. Okay. So all my, and I'm trying to find that in micrograms per millisecond, which is, I know, kind of weird, but that's typical gold standard. So this took me, I did this about an hour ago. It took me some time to play with it, but I slowly chip away at it. And just play the game. You got to end up with micrograms on top. There's no squares or square roots. That's nice. Micrograms on top, milliseconds on bottom. So the one on the test Thursday will either look more like this or more like the terminal velocity one. Okay, they're both nasty. But it's worth like 50 points. So it's worth your time. And it's worth your time to at least give it a shot. Don't, at this point, to me, I hate to say it, but you're kind of a fool to keep working at this point. I know some of you are perfectionists. You don't want to leave a problem until you finished it. You've got to get that out of your system. You got to learn when to cut bait, man. Move on, come back, fight another battle later. Okay, let's keep going and go to the next 2 or 3 problems, then come back. Because you don't want to get a 0 out of 20. And you know this is going to be blue. It's probably not going to be black, but it's going to be blue. So you're going to get half the credit back. I would stop here. So let's say it's worth 50 points. You'll lose, maybe you lose 6 points. You come back, and so you get a 44 out of 50. And then you come back with black and blue, and you get those 3 of those back. You end up with a 47 out of 50. Okay. So anyway, if you want to burn all the numbers, and now check me if you did this one. I always hesitate that I screwed up someone. There's my number crunching. All that's for 5 or 6 measly points. But there's all my numbers. I don't need units anymore because I took care of my units. I know it's micrograms per millisecond. And I think this is right. I do some green editing with the numbers too, to get rid of the big numbers. Okay, so unless somebody says I'm wrong, we'll call that good. You can check it tomorrow. Okay, so you all should get perfect scores tomorrow on your stamps, because that's it. All right. I didn't give you as much Easter eggs as I thought I might, but I'd take it. I just haven't written the daggone thing. Maybe I'll throw a couple more Easter eggs on the group meet tomorrow night. Maybe. Who has a question? We'll get you out of here in an hour. That's pretty good. Questions? Okay. Well, you guys certainly have a good night. And if you want to stick around and ask a question, you can. Otherwise, I'll see you guys tomorrow, hopefully. Okay, people are leaving. Okay. Uh-oh, Davy's on there. Davy, are you playing your video game? Davy's got a question.
No, I don't have any questions.
Oh, okay. All right, Davy. Then in that case, I'll see you tomorrow, my friend.
Okay, bye.
Bye-bye. All right. Stop this. Good old Davy. Good kid. Okay, let me stop this thing. All right. Hello. Oh, stop sharing. Okay. Stop the sharing. And now stop the recording. Oh, they changed their control panel. All right, we'll stop the scoring.